There's a couple of things I haven't mentioned before, but maybe you know. Up here at the top, we have these directive statements. These aren't necessary, like you don't have to include these. I like to include them just so that when you solve the program, it always is doing the same thing. But what these do is, there's different options. It'll set the units. In this case, so we could actually go down here and click this little area and set the units manually. But if you set it with this command, it'll just override these or update them. So you always want to be doing units that match. It's usually best to do it in like base units, I've found. This tab stop thing is not always obvious what this is doing, but this is just telling you if I hit tab, like I go through and I hit tab, the first tab that I hit is going to go 0.25 inches. The second tab I hit is going to go 2.5 inches. So if you wanted to format your code to look nice, maybe better than this, you can set the tab stop so that it does that. Okay. All right, so we have all the problem information here. Let's see, the units on the resistivity are ohm meter, right? Ohm meter. Ease knows what an ohm is in terms of base SI units, so it should all work out. It also has amps for current. So all that stuff is entered in. First thing is let's calculate the cross-sectional area, because that's needed throughout the problem. So cross-sectional area is pi d squared over 4. Again, that's the area that's available for heat flow in the direction of the wire, along the axis of the wire. OK, distribute nodes. So this is like step 1, right? We need to come up with our numerical mesh, right? So I'm saying here I've got 11 nodes. That's probably on the low end of what you might need. But it's just to get us started. So I've got 11 nodes. And in ease, what you're going to do is use a duplicate function. So I think, how many of you guys know what duplicate is or have used it? OK, not everybody. So what ease does is this is essentially like a for loop for ease. Really what it's doing is it's taking this equation that you've put in here, which is x, and then the square bracket with some index I. And then there's some function that depends on I in some way. And you're taking the contents of the duplicate loop and you're repeating it as many times as it takes to get across this range from 1 to n. So when ease interprets this, it's exactly the same thing as if I were to write out x1 equals this, x2 equals this, x, right? It's just a concise way of doing that. So you want to keep that in mind when you're coming up with the formulation. But duplicate is just a quick way of repeating equations, substituting the value of I for every possible value in the range. So we're going from 1 to n inclusive, right? 1 and n are both included in this range. We're getting our x1 through xn position just according to the equation that we had used, that we wrote before. So you have your duplicate and then end closes that. We're also calculating our node spacing dx, so that all should line up. And then we end up with the internal nodes. So this is the first thing that we did. So again, we're going to duplicate, but we want to be really careful about the range that we're using here. So the internal nodes, the equation only applies for 2 through n minus 1. Right? If you go in here and you say duplicate 1 to n, and then you provide an equation for 1 and an equation for n, it's going to complain that you have too many equations and not enough unknowns. Right? You're over-constraining the problem. So we will duplicate this for the nodes that are relevant. And this is hard to read, but if we looked at it this way, maybe is better. So here's our internal nodes. It should look exactly like what we had derived. You have KAC, you have our delta x, t, I minus 1 to t. So this is coming in from the bottom, or sorry, from the top. This is coming in from the bottom. Here's our generation term. Right? And we could double check and just make sure, we could just make sure that the units are OK, right, if I solve this. There's no unit warning, so in fact, it does work out, right? Let's go back here. All right, so internal nodes we have here. We're going to do the same thing for node 1 and node n. All right, so the workflow is you're basically entering 3 sets of equations: 1 internal node set, 1 node 1 set, and 1 node n set. So you have to repeat a lot of stuff, but it's now very specific to the boundary conditions that you're trying to enforce. So let's look back here, right? So again, it should be exactly what we came up with, T2 minus T1 as opposed to Ti, right? Here it's substituting n for 10, right? If it was being true to what we wrote, it would be Tn minus 1 minus Tn. But it's the same idea. Okay, so that's the entire formulation for the numerical problem. And you'll again note that like there are no there's no derivatives here. This is entirely an algebraic set of equations based on resistance, right? So let's solve this. Solve it. And what do we see? So here's a bunch of stuff. I guess what we're not seeing is anything relating to the temperature, right? We don't see a temperature profile anywhere. Because we use the arrays option, or the arrays nomenclature, where you're saying like T bracket I, that information is actually located in a different window. So if you go to Windows, Arrays, or Control Y, this is where we'll see our solution. And so any variable that we've used, like X bracket or T bracket, that stuff is going to show up here. Okay, so this makes sense. I guess we could look at it, right? Let's make sure it makes sense. We're going from Ti is 306. So that's actually higher than Th, right? But we have energy generation inside the wire, so maybe that makes sense. And then we're down to 56 at node 11. So I guess that all kind of looks about right. You probably want to plot this out. So we could, I've done that. Let me just show you how to do it, actually. So you go to plot, this new plot window. And then I have to select where I'm pulling this information from. Here I'm going to pull it from the arrays table. If you had run a parametric, you could pull it from parametric. So arrays table, I'm going to pick my x-axis and my y-axis. And then if you wanted to update every time you solve, you would do this automatic update thing here. If I wanted to add a legend item, it would be this one here. And then I'll click OK. Right? So that's our solution. I've actually done this already a little bit cleaner. So we have 11 nodes. I guess we're noticing something kind of interesting, right? That the temperature is going up before it goes down. I mean, there's thermal generation in the wire, so I guess that's possible, right? It's 1,000 amps we're trying to run through this thing. But yeah, so I mean, this is a solution. I guess it makes sense. What we could do is then go back and do an analytical solution. If we were able to, maybe we make a comparison there. You'll have to do something like that in the homework. Any questions on this? OK, yeah?
The 40 Kelvin temperature that we had earlier in the problem statement, that is at the node, or is that in the volume?
It's in the device that this wire is attached to. But there's a contact resistance between node N and the device. Right? So there's going to be a temperature drop there.
Right, so node N is at the wire, not in the volume.
Right, well, let's see. Yeah, so node, look back here. All right, so node N is in the domain, that the wire's conducting domain. We've drawn it here. It's at the edge of the very edge of the wire. But then there's an additional contact resistance after that that goes into the body. Yep. Yep. OK. Yeah.
So how do you determine mesh independence of the solution?
Yeah, so that's a great question. So what we would look at here is, let's go back. What is it that in this problem I actually care about? Do I really care about the temperature of the wire? Probably not, unless I'm worried about it melting. What I actually care about is, like I said, the heat flow from the wire into my experiment. So I'm going to add this equation down here at the bottom that says Q dot C, this is the heat flow into the experiment, is my temperature at node N minus temperature at node C divided by the resistance. Right? So this uses one of the temperatures that I've computed to calculate the heat load into the device, right? Sort of both of your questions. So this is actually what I care about. So I'm going to start varying my number of nodes to see if this value changes as a function of number of nodes. Right? So if I run this with 11 nodes, I see this Q dot C is 63 watts. That means my cryocooler has to supply this load at least. right? Let me go back. This is always dangerous to do it on the fly, but let me try it. So I'm going to add 101. Okay, easy problem. 63 watts. So it's still the same answer. 11 nodes is more than enough, right, for this. Now if I was going to do, I don't know, 3. 3 is the minimum we could do. I'll probably, so it's not bad, right? So, these are simple enough problems that we could talk about it quickly, but as you get to more complex problems, you'll find, maybe 50 nodes is usually okay, depending on your problem. Maybe 1,000 nodes is needed. Eventually, for ease, though, you run into limits and how many variables it can handle, right? And then we are really forced to use something like Python or MATLAB or whatever. Okay, there's one more thing I wanted to show, or 2 more things really quickly I wanted to show you. So let's see here. And that is, let's say I have some choice on how I design this wire. I'm putting together this experiment. I know I have to put 1,000 amps through the wire. I have 12 gauge, 14 gauge, whatever, all these different gauges available to me. So really what I want to do is optimize the diameter of the wire. There's maybe 2 ways that you would do this. So one would be, let's go back here to the equations window. I'm saying here, this is the diameter of my wire. Let's go and create a parametric table. I've already done that. And I'm going to enter some values that I have available. So I know I can buy from McMaster-Carr, whatever, all these different diameters. So I'm going to enter that in and run the table. I've commented it out. It should work. And I see that here's the heat flow into my experiment as a function of the wire diameter. Right? We could plot this as well. It looks something like this. So if I make the wire really, really small, what am I doing? Like, why is it going up? Well, I'm trying to run 1,000 amps through a really small area. And that just creates a ton of heat. So you're just basically heating this wire way up. Okay? There's a minimum. And then as I make the diameter larger, it goes back up again, right? Which means now this conduction along the axial direction from ambient temperature into my cryogenic region, that's becoming dominant. So you can use these to actually do a lot of this optimization for you, right? Now let's say that I didn't want to do a parametric table. I want to know exactly what this value is. You can also, again, go back to your window, comment out the thing you want to optimize. And there's a min-max functionality here. So min-max. It's hard to see. I'll unclick this stuff. So what this does is it will optimize a variable or set of variables for you, right, if you tell it the range that you want to look in. So what I want to do here is I want to minimize. So I'm going to click minimize q.c as a function of one independent variable. And why is it saying 1? Because I've commented one thing out here. So I don't have to do this in terms of diameter, but I commented it out and it makes sense, so I'm going to do it in terms of diameter. So I'll click that, and then I'm going to click bounds. And I have to enter in a lower and an upper bound that I'm going to allow this thing to search in. If you don't do that, it won't run. Okay. So lower and upper bound, I already did that, so I'll click OK. Max number of iterations, a tolerance, and I'm going to click OK. There are 2 different algorithms that you can use, the golden section and quadratic. They're both available. Click OK. Sometimes it'll take some time, but basically immediately it decides the optimal diameter is what? 0.8 or 8 millimeters, 8.6 millimeters. Okay. So that should probably line up with what we saw in that plot, right? Yeah. So either manually doing this by a parametric table or doing it by the min-max functionality they both give you the same result. Right? Okay, that's all I had for today. Thanks.